Thank you. Recording in progress. Alright, that's what we call traditional dance from West Java. We call it Tari Merak or Peacock dance. Has a meaning, welcoming special guest for today. Alright, Bismillahirrahmanirrahim, let's start this event. Assalamualaikum warahmatullahi wabarakatuh. Sampurasun. Good morning, ladies and gentlemen. His Excellency, General Secretary of Badan Kerjasama Teknik Mesin Indonesia, Profesor Dr. Aryo Baskoro MTMA, the respectable Chairman of the Committee, Dr. Insinyur Ade Bagja MMA, the Honorable our keynote speakers, Professor TM Indra Mahlia from University of Technology, Sydney, Australia, and Professor Dominic Perix from University of France participants. First of all, let's praise the Almighty God. For His blessing, we are able to attend this international seminar held by Badan Kerjasama Teknik Mesin Indonesia. And I am Dahlia Rineva as your Master of Ceremony for today. Ladies and gentlemen, our first agenda is sing the national anthem, Indonesia Raya. Ladies and gentlemen, please stand up. Have a seat. Ladies and gentlemen of committee, Dr. Insinyur Ade Bagja MMA, the time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi. Salam sejahtera bagi kita semua. Salam. Om Swastiastu. Namo Buddhaya. Sampurasun. Nah, kita pemanasan dulu, kita ulang. Nah, Bapak Ibu izin kalau orang Sunda, Jawa Barat, pembukaan itu biasanya pakai sampurasun. Nah, jawabannya rampes gitu. Mohon izin, biar semangat semuanya, saya sampurasun. Nanti Bapak-Bapak dan Ibu tolong jawab dengan rampes ya. Oke. Sampurasun. Alhamdulillah. Terima kasih, terhormat Bapak Rektor Universitas Pasundan beserta Dekan Teknik Mesin atau yang mewakili, yang terhormat Profesor Dr. Aryo Sunar Baskoro SNTTM sebagai keluarga besar BKS-TM, pengurus BKS-TM yang tidak bisa saya sebut satu persatu. Distinguished Professor, Keynote Speaker, Profesor Dr. Teguh Merah Indra Mahdia yang nanti akan bergabung dengan kita di Zoom. Distinguished Keynote Speaker, Profesor Dominic Peru, Bienvenu a Bandung, Prof. Lalu yang terhormat Dr. Insinyur Sugiharto MT, Dr. Insinyur Dedi Lazuardi, beserta para panitia seminar SNTM 21 dan Port ISAIME 2023, serta yang kami banggakan para pemapar dan peserta di seminar SNTTM 21 dan Port ISAIME 2023. Perkenankan Bapak dan Ibu, saya membuka sambutan ini dengan sebuah pantun. Mudah-mudahan pantunnya benar karena saya lagi belajar untuk bikin pantun gitu. Kacai jadi saluwi, kadarat melak kalapa, kuring rek menta widi, eker nyambut ieu acara gitu. Mohon izin bahasa Sunda Bapak Ibu gitu ya. Tapi artinya adalah izin saya akan membuka sambutan daripada seminar SNTTM dan ISAIME ini. Para hadirin yang terhormat, saya memperkenalkan diri Dr. Insinyur Ade Bagja MME sebagai koordinator atau chairman dari acara seminar ini akan melaporkan secara garis besar apa yang akan kita lakukan atau kegiatan utama yang akan diadakan pada hari ini. Gitu sebetulnya hal-hal intinya sudah disampaikan oleh Pak Dedi kemarin dalam musyawarah anggota BKS-TM. Yang pertama, tema yang diusung di dalam seminar ini adalah Improving Mechanical Engineering Resources and Technology Capability for Facing the Challenge of Industry 4.0. Field atau bidang yang akan dibicarakan cukup beragam, Bapak dan Ibu semuanya, gitu. Mulai daripada manufacturing, mechanical engineering education, untuk mempersiapkan acara ini, dan beliau mengatakan animo yang ikut dua kali gitu. Ini yang terjadi adalah ternyata total paper yang masuk jumlah totalnya itu adalah 238 paper. Di mana SNTTM-nya 150, ISAIME-nya adalah 88. Ini Prof. Aryo disampaikan, bahkan sampai hari kemarin, bahkan kemarin malam masih ada yang nanya, boleh nggak saya submit lagi? Udah saya bilang udah cukup. Udah ruangannya nggak ada, kita juga perlu preparasi dan sebagainya. Jadi mohon maaf kepada Bapak Ibu atau koleganya yang bukan untuk menolak, bukan, tapi karena keterbatasan waktu yang tersedia. Saya berpikir dengan teman-teman kalau menyebutkan universitasnya atau perguruan tingginya kebanyakan nanti kita ganti saja gitu ya, anonymous gitu ya. Bagaimana kalau kotanya yang disebutkan ternyata setelah kita tabulasi itu mewakili kebinekaan Indonesia dari Sabang sampai Merauke. Saya sebutkan kota-kota yang menjadi asal daripada perguruan tinggi yang submit di paper ini. Mulai dari Banda Aceh, Lok Sumawe, Medan, Padang, Riau, Pekanbaru, Lampung, Bogor, Jakarta, Depok, Bandung, Cirebon, Surakarta, Jombang, Surabaya, Malang, Ponorogo, Bangkalan, Samarinda, Makassar, Manado, lalu Ternate sampai dengan Jayapura gitu. Jadi dari ujung barat sampai ujung timur ikut semuanya. Jakarta, Depok. Nah, bahkan gitu. Bahkan Northwest Polytechnical University. Nah, Bapak dan Ibu tidak semuanya dari perguruan tinggi karena bukan apa-apa. Ada sivitas institusi riset yang ada di Indonesia juga yang ikut dari BRIN. Ada beberapa paper dari BRIN. Nah, kami ucapkan juga sama. Jadi kita memang kumpul bareng semuanya yang terkait dengan mechanical engineering gitu. Nah, ini juga kami laporkan untuk jumlah paper yang jumlahnya 238 ini, reviewernya yang utama 7 orang, lumayan belenger meriksanya gitu kan ya. Tetapi alhamdulillah kita dibantu oleh beberapa reviewer yang lainnya gitu. Nah, ini juga tadi saya ngobrol sebentar dengan Pak Aryo gitu kan ya. Saya nakut-nakutin beliau, tahun ini kita jarang dengan 238 paper gitu kan ya. Mungkin 4-5 tahun lagi jumlahnya akan bertambah. Saya sempat ngitung-ngitung gitu kan ya. Ngitung-ngitungnya gimana gitu kan ya. Kalau sekarang aja anggota BKS-TM itu katakan misalkan dari 165 totalnya gitu kan ya, yang masuk adalah 236 paper. Kalau kedepannya, kalau semuanya ikut memasukkan 2 atau 3 paper, maka tiba-tiba Pak Sekjen akan nerima 500 paper. Mangga nyangakeun Pak Aryo. Banyak gitu aja. Nah, itu satu sisi dalam hal jumlah paper. Yang kedua, pada saat pengalaman kami mengcollecting pengalaman para reviewer adalah ternyata bidang teknik mesin, bidang mechanical engineering sudah berubah demikian jauhnya. Udah berbagai macam luas sekali. Ada berbagai penambahan-penambahan. Ada di sini yang ada saya contohkan adalah ada beberapa orang peneliti kita gitu yang ada di perguruan tinggi itu yang berjalan dengan yang namanya biomedik atau biomekanik gitu. Pada saat kami mereview gitu kan ya, kami santai-santai saja. Itu ada beberapa paper yang terkait dengan implan gitu. Pada saat implan ada yang berbicara tentang yang namanya desain atau perhitungan kekuatan implan dan sebagainya. Saya bilang ke teman-teman gampang cincai, itu untuk orang mechanical engineering udah hal kebiasaan sehari-hari gitu aja. Tetapi ada paper yang mengatakan bahwa judulnya aja saya baca gitu ya biar sama-sama ngeri teman-teman gitu ya, adalah bagaimana pengaruh proses manufaktur magnesium sebagai implan terhadap toxicity dan viability sel tubuh manusia. Nah, begitu baca itu menjadi tidak biasa gitu kan ya. Karena yang dibaca juga sudah mulai berubah, udah mulai ada istilah medis, kedokteran dan sebagainya. Yang kedua, ada yang lebih menakutkan lagi. Serem gitu ya. Orang mesin kalau bicara drilling pasti tahu semuanya lah. Mau dia keahliannya konversi, konstruksi atau dan sebagainya. Drilling tahu gitu kan ya. Ujuk-ujuk muncul sebuah paper yang bicara tentang bagaimana melakukan proses drilling pada tulang manusia. Kebayang nanti suatu saat bapak-bapak gitu kan ya, yang namanya ruang operasi itu yang namanya bengkel mesin bubut pindah ke bengkel operasi ke operasi ke tempat bedah gitu aja. Nah, ini juga kita mesti mengantisipasi karena bukan apa-apa. Nanti akan muncul paper-paper yang memang di luar jangkauan nalar pada hari ini. Berubah jauh gitu ya. Belum muncul yang namanya nanoteknologi Prof Aryo gitu ya. Belum muncul lagi yang lain-lainnya, belum muncul lagi yang namanya aditif teknologi dan sebagainya. Nah, ini kedepannya akan bertambah lagi pengetahuannya. Jadi, itu yang bisa kami laporkan. Nah, itu adalah prospek kedepannya yang akan kita hadapi. Nah, kami juga mendengar kemarin pada saat musyawarah anggota bahwa BKS-TM akan mempunyai yang namanya lembaga publikasi. Ini memang dibutuhkan, Pak. Gitu aja. Karena dengan semakin banyaknya kita nulis, semakin banyak orang berkarya, maka perlu yang namanya lembaga seperti itu. Nah, masukan yang kami masukkan adalah mungkin perlu yang namanya standarisasi reviewer dan standarisasi daripada kualitas publikasi. Ini yang akan membuat kita BKS-TM menjadi semakin jaya ke depannya gitu. Hari ini juga kami berterima kasih bahwa kami ada 2 keynote speaker. Satu adalah Profesor TM Indra Mahlia dan satu lagi Profesor Dominic Perlu. Nah, seminar ini, jadi Bapak Ibu semuanya, seminar ini akan dilakukan dengan 7 kelas paralel dikali dengan 3 sesi, pagi, siang, dan sore, yang akan dipandu oleh moderator dalam setiap sesi dan kelas paralel tersebut. Bapak Ibu, probably this is enough that I can deliver on this occasion. Tidak ada gading yang tidak retak. If there is any mistake during the seminar, on behalf of organizing committee, thank you very much, and I would like to welcome all the presenter in this seminar. Enjoy the discussion. Selamat berseminar. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Dr. Insinyur Ade Bagja MMA, as the chairman of the committee for the review of the session of the next agenda.
Universitas Pasundan, Profesor Dr. Insinyur Haji Edi Yusuf SPM SIM, our Honorable Profesor Dr. Insinyur Yusman Taufik MP, Dean of Faculty of Engineering, Universitas Pasundan, our Honorable Dr. Sugiarto STMT, Head of Mechanical Engineering Department, Universitas Pasundan, our Chairman of Committee, Dr. Insinyur Ade Bagja, MMA, Your Excellency, our distinguished keynote speakers today, Professor TM Indra Mahlia, Distinguished Professor Center for Green Technology, School of Civil and Environmental Engineering, Faculty of Engineering of Technology, Sydney, Professor Dominic Perou, Université de France-Comté, all guests and participants, ladies and gentlemen. It is both a pleasure and honor for me to welcome you to the 21st SNTTM in conjunction of the 4th International Symposium on Advances and Innovations of Mechanical Engineering in Universitas Pasundan, Bandung, Indonesia. Badan Kerjasama Teknik Mesin or BKS-TM, or in English is Indonesian Consortium of Mechanical Engineering Higher Educations, is a consortium of mechanical engineering study program established in May 29th, 2002. So this year,
recording in progress.
showcase our scientists and researchers
Professor Dr. Aryo Sunarbaskoro, please stay on the stage because after this one we are going to giving appreciation for the chairman of the committee, Dr. Insinyur Ade Bagja MME. So we would like to invite Dr. Insinyur Ade Bagja MME. All right, this is the appreciation for the chairman of the committee from General Secretary of Badan Kerjasama Teknik Mesin Indonesia. Thank you very much, and please have a seat. Ladies and gentlemen, before we break, we are going to move to our main agenda, Seminar International, and the seminar will be guided by moderator Dr. Insinyur Ade Bagja MME. To Dr. Insinyur Ade Bagja MME, the time is yours.
Ladies and gentlemen, please allow me to open this seminar. Welcome.
Baik, kami informasikan sebagai
paper itu memperoleh lebih daripada 1.800 citasi. Banyak sekali, gitu ya. Lalu lebih lanjut menurut Scopus, Profesor Mahlia ini mempunyai isi lebih daripada 28.000, yang menjadikannya beliau mendapatkan penghargaan sebagai apa? Sebagai peneliti dengan citasi tertinggi pada tahun 2017 sampai 2022. Dedikasi yang lain daripada Profesor Mahlia ini adalah menularkan ilmu dan pengetahuan yang dimilikinya dengan mendidik dan melakukan supervisi kepada sejumlah mahasiswa program doktorat dan sarjana. Ini jumlahnya tidak saya sebutkan karena terus bertambah dari waktu ke waktu. Saat ini Profesor Mahlia merupakan salah satu dari dalam program World Class Professor di bawah Kementerian Riset dan Pendidikan Tinggi Republik Indonesia. Dan juga beliau termasuk ke dalam Dewan Editor Jurnal Research in Ecology yang diterbitkan oleh Bilingual Publishing Corporation. Rentang bidang fokus daripada penelitian Profesor Mahlia ini sangat luas. Itu mulai dari energy and fuels, techno-economic analysis, water life cycle yang lagi populer, circular economy. Saat ini Profesor Indra jadi contoh buat kita yang sangat baik. Prof Indra.
Yes.
Yeah, time is your, Prof. Please.
Okay, thank you very much, Mr. Moderator. Firstly, I would like to thank the organizing committee for inviting me to this conference. Even though now my post under civil engineering, my first degree, master and PhD under mechanical engineering atau teknik mesin. But here, my research, which is related to energy and fuel, biofuel, liquid fuel, related to civil engineering. So they put me under civil engineering. Bisa dengar, Pak?
Cuman mungkin mohon izin Bapak dikurangin kecepatannya karena terkait dengan jaringan, Pak.
Okay. Baik. The title of my presentation today is about fuel economy standard and labels for sustainable transport. This due to because in Indonesia, as far as I know, we still don't have this fuel economy standard that's make Indonesia become a good market for inefficient vehicles. So I think it's very in time for Indonesia to implement this program. And as you know, this world has changed a lot since industrial revolution, and we emit tremendous amount of emission due to our activities, and this can be observed by global warming, which is you can feel now. Even in Bandung last time a bit cold, now it's become quite warm. One of the activities that contribute to climate change is the energy generation, which is including our transport. And one of the solutions is to use energy resources efficiently. This, as you can see here, the primary global energy consumption is mostly for electricity, and then for transport, industrial and residential and commercial. For our case here, for transport is about 30%. And for these case, developing countries often bear the burden of accommodating inefficient vehicles because we don't have what they call energy efficiency standard. So by enforcing fuel economy standard can serve as barriers against the entry of inefficient vehicles into the country, which is implemented in developed countries, including Australia. And for the car, the thing that can be improved is based on the losses. The energy balance of the vehicles, as you can see here, is 72% is engine losses, and only 17 to 21% the power of the car transfer to the wheels. So it's a lot of improvement can be done here. So in order to win the market, usually the vehicle manufacturers, they improve the efficiency and they put the thing as energy labels in the windscreen of the vehicle that stated the efficiency vehicle. Hopefully the most efficient vehicle in the market. The hierarchy of the fuel economy standard, or we call it fuel economy, is actually the foundation of this fuel economy is the test procedure, where with this test procedure we test the car based on their efficiency. Then based on the efficiency, we set the fuel economy standard. Car with certain efficiency can enter our market. Like to put in a very simple way, like a student can only graduate with GPA 2.0. So only the car with certain efficiency can enter our market. So we don't have to they don't have to use our resources, especially oil, inefficiently. As far as I know, for a long time, Indonesia have to subsidize the oil, and then based on this fuel economy, we set the fuel economy labels. The label is actually just a sticker to put in the windscreen of the car to grade the car according to their efficiency. And at the top of the this pyramid is incentive program, which is usually government give incentive to consumer to buy the most efficient car. Okay, like in Australia, if you buy efficient car, you will get about 2,000 to 4,000 incentive. The other incentive is to manufacturers who produce a more efficient car. So they have manufacturers to advertise the vehicle that efficient. If you want to know about this thing deeply, you can follow in this paper published in 2001, which is talking about deeply the equation that we use to calculate the impact of the implementation of this program. So I will not present this one here because a lot of action is not suitable for a keynote speech. And the test, as I told you, the fundamental thing of this program is the test procedure. A test procedure is actually a procedure that to determine fuel economy and emission of the vehicles, usually in the kilometer per liter or liter per kilometer or in mile per gallon. As you can see here it's the structure is like this. Then you put the car and this dynamometer here, and this we calculate sample emission. Because in some countries they use emission as a standard. If the car emit more than the standard, the car cannot enter the market, or they have to pay the penalty. There are two ways to do this: to decrease fuel consumption, or to use the catalytic converter. That's why some of the car like Volvo, they use catalytic converter. Here, what I want to share in 4-dimensional, this test procedure, which is, we have a video here.
Halo, Prof Indra.
Yes.
Sudah enough? Oh, you have more? Sudah cukup belum, Pak?
Well, I'm presenting. Hello?
Halo, ya Prof.
Ya, gimana Pak?
Apakah sudah cukup menyampaikan keynote-nya atau masih ada yang mau disampaikan?
Masih ada Pak. Berapa lama waktu untuk saya Pak?
Masih 15 menit, Prof. You have still 15
Masih 15
minutes to go.
No, this I'm sharing the video. Can you see the video?
Please. You still have 15 minutes to go.
All right. I'm sharing the video. question? Yes, that's the I don't know if you can hear the video or not. Okay, let me continue. These some countries that have introduced fuel economy standard and emission. There are actually 3 test procedures that Can you see my slide bar?
Yes.
Can you see my slide? Okay.
Yes, we can. But it's not so clear. It's blur.
Is it okay now?
That's correct now.
Okay. This one, actually there are 3 types of test method that widely used in the world. The first one they call it US cafe. The second one European test procedure. The third one is Japanese test procedure. As you can see here, different test procedure using different type of the grade of efficiency. In the United States, they use fuel. In European Union, they use the CO2 emission. And in Japan, they use fuel. In California, they have the different test standard. They use the greenhouse gas. So if Indonesia want to adopt the test procedure, they should adopt this 3 rather than develop their own test procedure, because it's a bit difficult. And in some country, mostly the car that enter the country can be implemented as mandatory or voluntary. So depend on the country. But based on the other country experience, for this case, India, voluntary, it doesn't work because most of the car doesn't want to test their vehicle if they are not efficient. And this the test procedure that used in the United States, as you can see here, it's the car have to travel about 18 kilometers and have to follow this structure. Usually they use robot to drive the car accordingly. And the duration about 30 minutes. So based on that, we measure the efficiency of the car. This is the test procedure of the European test procedure. So we have to repeat this one for 3 times. About 1,200 seconds, and the distance about 11 kilometers, with average speed of the 33 kilometers per hour. And this one, Japanese test procedure, since the car, more than 80% of the car in Indonesia using Japanese car. So if you want to implement this fuel economy standard, the most suitable to adopt is the Japanese test procedure, because we don't need to retest the car. So we just put the labels on the car. And the paper about test procedure you can get online. This discuss deeply about how to implement and what to do with this, how to deal with this test procedure. And based on the test procedure, then we implement fuel economy standard, where fuel economy is actually the average distance traveled by the car or vehicle for 1 liter of fuels, usually in kilometer per liter or liter in per 100 kilometer, or in US they use in mile per gallon, where fuel economy standard are a regulation that prescribe the vehicle's fuel economy levels as a criteria that manufacturers must meet in order to get permission to sell their vehicles in a certain market, for example, Asian, Indonesia, or Malaysia. As you can see here, in China now, if you want to send the car, you want to sell the car in their market, in 2020, the car must reach 5 liters per 100 kilometer, but in 2030, about 3.2 liters per 100 kilometer. Only Prius can achieve this, Toyota Prius can achieve this fuel economy. And same certain efficiency in order for you to be permitted to sell the car in their country. This fuel economy emission is standard for passenger car in selected country. As you can see here, many countries have implemented the program mandatory. So the car must be tested mandatory, then you achieve minimum efficiency, then you can sell the car in their market. So in United States, they use mile per gallon, and European Union, they use gram per kilometer of emission. In Japan, kilometer per liter. In Australia, we use liter per 100 kilometer. The car less than 600 kilogram, the car must achieve fuel economy 4.44 liter per 100 kilometer. And if the car more than 2.2 tons, must achieve 13.51 liter per 100 kilometers. This is in United States. As you can see, after the implement fuel economy standard, the car efficiency improved almost double from 15.7 in 1978 to 7.2 in 2012. So almost half. Comparison of fuel economy emission standard in selected country. Now it's from here, it's going down, as you can see here. The slickest now is China. It's going down. They're following this one. So the fuel consumption must be around 4 liters per 100 kilometers if you want to sell the car in China right now. This is a comparison fuel economy standard in some selected countries. In United States, you must achieve the emission 143 grams CO2 per mile. In China, state 5, you have to have 4 liters per 100 kilometer in 2 years if you want to export the car to China. This, even in India, they said already in 2021 for small car must achieve 4.7 liter per 100 kilometers or equal to 113 gram CO2 per kilometers. So it's very strict now. And this some discussion about this thing you can read in my paper published in 2010 on fuel economy standard for motor vehicles. And this is fuel economy labels. This label is actually a mandatory or voluntary sticker that affixed to the vehicle containing information about the fuel economy of the vehicles. So when here in Australia, when you go, you buy the car, you will find this thing in the windscreen of the car. So I will share the video about this thing. This one may be good.
If you want to sell more cars, making yourself more money in the process, then the fuel economy label can help you do this. Your customers are looking to save money so they can go further on a tank and save on their ongoing fuel bills. The fuel economy label and the information it shows can help them make an informed choice and feel good about it, which can help your sales as a result. So the label acts as a sales tool for you. By understanding what your customers want, you can help them and yourself. The label shows important information car buyers look for to make their decision. For 7 out of 10 of your customers, fuel consumption is third only to price and reliability when it comes to what is important to them. Talk to your customers about reliability and price, but remember that 70% of people are also keen to know about fuel consumption. And this is where the label comes into play.
I've had Jags, I've had Porsches, I've had the lot. You sit at the traffic lights and you're a big, powerful car and people are looking at you going, well, there's a greedy, selfish person. Is he using more fuel than he should be? When I started looking around, I thought, well, I don't want to lose the performance from a motor vehicle, but I also don't need to be outlaying all that money on a monthly or weekly basis.
I bought a car last year and I can honestly say it was the very first time that I bought a vehicle and had a concern for the fuel consumption of the vehicle, because with petrol, the price that is at the moment, the last thing I want to do is waste a fortune of my hard-earned cash on filling up my car.
Consumers being able to find out
The cost of what that vehicle's expenses are going to be over the course of a year, and I think that that's really handy information for a consumer to have.
The label allows people to compare similar vehicles with similar features and easily find out which offers them the best fuel efficiency and lowest running costs. Different aspects of the label appeal to customers in different ways. Let's take a closer look. This number gives an estimate of how many litres of fuel the car will use to travel 100 kilometres. The stars on the label show car buyers the fuel economy rating. It gives a rating out of 6 stars, and the more stars a vehicle has, the better its fuel economy. And this tells them the average running cost per year. Fuel prices can change regularly, so the cost per year is calculated with a set fuel price. As the fuel price is the same across all labels, people can compare vehicles, which can help you make the sale.
Well, we're seeing an ever-growing interest from customers in the fuel economy of vehicles, particularly with the increase in fuel prices over the last few years.
More and more people are coming in wanting to know how fuel efficient our cars are, and of course we can just show them, there's the car, that's how economical they are, and of course because it's not our actual figures, people do believe them.
I use the fuel economy label as part of my sales presentation. It helps us identify customers' needs and the products that's going to best suit their needs.
Well, the motor industry is moving towards hybrid cars and more fuel-efficient cars.
If we as salesmen don't keep up with that and keep motivated with those changes, we're going to miss out on opportunities.
Fuel economy labels are available for the following: used and new light vehicles, cars, utes and vans, vehicles under 3.5 tonnes, and vehicles manufactured from the year 2000. Accessing and creating the label is easy for you too. All you have to do is visit fuelsaver.govt.nz and follow the steps. There is even a simple step-by-step guide for you on FuelSaver if you are having trouble generating a label. The label is generated as a printable PDF file on your computer for you to open up and print.
Sorry, Prof. You still have 5 minutes remain.
Okay. Thanks. Right. Let's continue. This is the label, and this is UK energy labels. Like as you can see here, it's in the gram per kilometers. And this is Australian energy labels. We use both 12 liter per 100 kilometer and the emission as well. But it's a bit difficult for this case, a bit difficult when you compare the car with different CC. So you think a small car, they are inefficient. It's tend to lower the fuel consumption and emission. So it's actually These are US energy labels in mile per gallon. And this one, quite good, but a bit difficult for laymen to understand. This Singaporean energy labels, its fuel consumption and the emission. And a good thing here, as I told you earlier, it's intensive here, intensive program where the car will, they call it in Singapore fee base and amount, which is the customer will get discount about $15,000, or if the car inefficient, we get penalty. But a bit difficult to laymen to understand the whole labels. This is the New Zealand energy labels, and this is Japan energy label. Very simple. It's means this car, I think, 20% more efficient than average. This one, Brazil energy labels in fuel consumption here, kilometer per liter. This South Korean energy labels. So they use a number here. Here, the most efficient one. This is Thailand energy labels. And this, the history of the fuel economy labels. It's actually this thing first implemented in not in the US but in the Poland but they use for electrical appliances in 1962, I think. But the one who implemented for vehicle first is the US, and this all the country that's implemented energy label except Indonesia. We are waiting. I hope will be implemented soon. And this some of the one of my paper on history of current status of energy labels and implementation in Malaysia. And the last one is an incentive program. In the US, they have what they call gas guzzler, where the car with inefficient car will be taxed by government. For this case, for this case, at least 22.5 miles per gallon, no tax. But after that, the car will be more expensive because of the tax. This US emission tax, if the car emission is this amount, there is no tax. But if you reach this one, you have to pay the tax 12% of the price of the car. These two categories of incentive program. The first one, incentive program for manufacturers. Usually what they do, they advertise the efficient car, tax exemption, import duty exception, and incentive for the buyer, road tax reduction. Here we implement this thing, and soft loan for efficient car or rebate for electric vehicle, which is we have here in Australia. And this some one paper on the incentive program, which you can download online. So because now our era is electric vehicles era, actually there are three types of electric vehicles. The first one like hybrid, which is we don't really use electric actually. It's powered by both engine and electric motor. The battery is charged internally through the engine, and the second one plug in like this one maybe like Toyota hybrid, and this one is like a Mitsubishi Outlander, where you can plug in, you charge it, but you cannot travel so long. I think around 100 kilometers with electric. And the third one is all electric vehicles like Tesla. So we divide into three. And of course, they have different benefit here in Australia. And this is the leader of electric vehicles in the world. In 2040, it's about 60 million electric vehicles will be in the market, and lead by China, of course. And there are test procedures as well for electric vehicles, but the only difference is instead of using fuel consumption or liter per 100 kilometer, we use watt-hour per kilometer or watt-hour per gallon for electric vehicle. The test almost similar, that just we measure different things. This electric vehicles label in Australia, as you can see on its boost electric energy consumption in watt hour per kilometer, and range the distance in 160 kilometer for this case. This is electric energy labels in the US. A bit complicated, it's difficult for layman to understand. Only engineer can understand this thing, I think. And this electric energy label in New Zealand, the range, and this one electric vehicle.
Prof.
Kilowatt per
Mahlia,
100
sorry,
kilometers.
1 minute,
Yes.
Prof.
All right. But unfortunately in Australia, the top performer of the car and top seller are two different things. This one, the most efficient car in this side. But the one who, the top seller in the market is Ford Ranger here. Because Australia terrain is quite, almost everyone here have this 4x4, four-wheel drive vehicles because of the environment. So sometimes what you want and the performer of the car and the top seller is quite different. The conclusion is standard labels are the most effective way to improve fuel economy and reduce emission from the transport sector. And standard label increase the competitiveness of an efficient vehicle or brand here in international arena, safeguarding our market against the influx of inefficient vehicle by implementing the fuel economy standard. So we don't have to, now we subsidize the oil, later on we have to subsidize the electricity for inefficient car. I think that's all from me. Thank you very much.
Thank you, Prof. Mahlia. But I would like to ask the audience, either their Bapak Ibu, ada pertanyaan untuk Prof. Mahlia? Nggak ada? Oke, nggak ada ya? Oke, Prof. Mahlia, actually I have a small question for you. Is there any relation between the fuel economic standard with the driving profile of the driver itself?
Of course, if you talk about efficiency, there are two things. If you have efficient car, but you drive inefficiently, there is no energy saving. But
yeah,
even
I
if
heard
you
there's a huge discussion, Prof, between the standard procedure itself and also the driving profile, because the driving profile is really different with the procedure.
The thing is, for this fuel economy standard, we assume the way you drive, the road, everything is similar, business as usual. Just we only consider the car, not the behavior of the driver.
Okay, thank you so much, Prof. Audience, please give the applause for the professor. Thank you so much, Professor. It's a really interesting topic.
Thank you very much for having me.
Thank you, Prof. Prof. Mahlia, if you would like to stay on Zoom, please, because we would like to go to the second keynote speaker. So you are welcome to still join, or if you have something else to do, you can leave also. Which one you like, sir?
Okay. I have to go to my office. It's actually right now I'm at home. So I'm leaving now.
Okay.
Thank you.
Again, thank you so much,
for having
Professor
me.
Indra Mahlia. Thank you so much.
Thank you. Bye.
Bapak Ibu, saya
is over 100 million of degree. And so due to this, it's not possible to take the gas inside a tank. So we need a magnetic field. And to get this, we need a no-magnetic pre-compression ring to maintain the structure by itself. And you can see on the figure a big ring made with composite materials. For this ring is about 3 meter length in diameter. And so the thickness is about more than 20 centimeters. So it's a big deal to perform this kind of pre-compression ring. Next slide, please. So now I would like to speak about the problem of electricity storage, and especially to show you how some advantage with hydrogen that we can have. So next slide, please. So why hydrogen is interesting to store electricity? Sorry, it's again in French, because you can compare different kind of way to store energy. Of course, for short time, you can use a super capacitor, or you can use a battery. But in this kind of device, you are limited in energy, and you are also limited in time to store this electricity. And one advantage of hydrogen is that you can store a lot of energy, and also you can store this energy for a long time. And so this is one of the main interests of hydrogen, is to store a big amount of energy, and also to store for a long time, for instance, for the winter, from the summer to the winter, if you produce energy with sun, for instance. Next slide, please. Okay, this one. Okay. Here is economic place of hydrogen today. You can see on this figure the growth of energy compared to the growth of energy of hydrogen used from chemical point of view. It is not clear here, but the figure here, it's a chemical energy. Yeah, the figure here, it's the white part is chemical energy, and it's almost the same. And when you go to the times, you have more and more use of hydrogen in different sectors. And we assume that in about 30 years, about 20% of the energy will be used hydrogen. Here is a project that there is in the world. And you can see that if you compare the project in 2020 compared to 2023, the project is always increase and drive that there is a big interest for hydrogen today in the world. And it's even in Indonesia, you have already some project, because your highland is very promising to this use of energy. Next slide, please. It is strange, but hydrogen has a lot of color. This color is not real color of the gas, of course. It's color to speak about the type of production of hydrogen. So here you can see that the black hydrogen, the brown hydrogen, the gray hydrogen, and the blue hydrogen is made with fossil fuel. And today, about 95% of the hydrogen is made by first fossil fuel. So it is not like that we would like to produce in the future. In the future, we assume that the main source of production will be use electrolysis with water, and maybe nuclear energy or renewable energy. So energy without greenhouse gas. And so today in Europe, there is a big competition between nuclear energy and renewable energy between France and Germany, because we are not agree about that point. And it's a big difference between our country. So in the future, we assume that yellow hydrogen or green hydrogen will be most of the hydrogen that we can produce. There is also the possibility to use white hydrogen, Because in the past, we assumed that there is no hydrogen on Earth. In fact, more and more people find there is some hydrogen on Earth, and we assume that it is possible to capture this hydrogen for the future. Next slide, please. So I want just to give you some figure about the interest of hydrogen with energy. If you compare energy that you can have with hydrogen to other fuel cell, to other fossil fuel, you can say that hydrogen is three times energy than fossil fuel. But there is a big problem with hydrogen. You have only 50 grams per liter at 200 bar and 20 degrees. So the problem of storage is a huge problem because if you compare, you have 3 times energy, but you have only 50 grams of hydrogen in a liter. So it's not like that you can use this hydrogen. Next slide, please. So this is why we assume that if you have, because we have 3 times of energy and because electrical engine is 2 times efficiency than the thermal engine, we can assume that with 1 kilogram of hydrogen, it is enough to perform 100 kilometers. So if you assume that you want a car with 500 kilometer range, we need to have a tank, and this tank will be 330 liters. So it looks like a big tank if you transport your hydrogen at 200 bar. And 200 bar today is the way to transport hydrogen in a metal tank. Next slide, please. So now if you want to design this tank, you need to understand what is the stress that you have in this tank. So it's an elementary calculation. You can see that you have axial stress and you have hoop stress. Usually, hoop stress is 2 times higher than the axial stress. This is why when you look at how you get a failure of a tank, the failure is always in a hoop direction. So you design a metal tank in function of this hoop stress. Next slide, please. So, of course, when you design a tank, you need to take a safety factor. So first, we use a safety factor which is common factor, but it is called for Transportable Pressure Equipment Directive, and the safety factor is about 2. When you have this hoop stress and when you have this safety factor, you can design this tank and find at the end, find the thickness of the tank. And you can see here, for this tank, at 200 bar, the thickness is 10 millimeter. At the end, the mass of the tank is about 280 kilograms. So if you compare the mass of the tank to the mass of hydrogen you transport, you are around 1.75%. So you transport mainly steel and not gas. So this is why if you want to transport hydrogen, especially for long distance, and especially if you want to use hydrogen for car, it's not possible to use steel tank. You need to use materials with higher strength. Here the strength of the steel is not enough for this application. So you need to use a composite material, and composite material with higher strength. Next slide, please. So here, usually there is some animation, but here you have here the position of pressure tank at room temperature, and it is here. And you can see that if you increase the pressure up to 700 bar, you can get not 50 grams per liter like you have at 200 bar, but 40 grams per liter like you have at 700 bar. So for car, most of the tank today are used at 700 bar and use the composite materials. Of course, there is other way to transport hydrogen. You can use the metal hydride, you can use borohydride, you can use other kind of, you can use also NH3. What's the name of NH3? I don't remember. So it's a chemical product, very famous, and ammonia. Sorry, it's ammonia. But in fact, if you use this, it doesn't work for a car. So the only way for a car is today is to use a pressure tank. Next slide, please. So this is why, if you use pressure tank, this is why we expect a big growth of carbon fiber in the future, because the requirement of carbon fiber, and especially high strength fiber, will be dedicated to this pressure vessel. Next slide, please. There is there is 5 types of tank today. The first one is a pure metal tank. This is the one we discussed. And more composite is used in this tank. So at the end today, what we call type 4. Type 4 use a polymer liner and also a composite structure to resist to the pressure. And so the difference between type 1 and type 3 is you separate the function. In type 1, the metal is against the leak or permeation and also against the pressure. Here, for type 4, the liner is against the permeation and the composite is against the pressure. So you have a separation in this technology of the function of the tank. And with this kind of tank, especially type 4, today we can get about 6 to 9% of hydrogen inside your tank, and the tank at 700 bar. So it's, I would like to say, about 4 times efficiency than a metal tank. Next slide, please. So it is how we produce this tank today. Usually we should have an animation of this figure, but here it doesn't work. So you can see a filament winding machine where you have a liner, and around the liner you have the filament of composite fiber. Next slide, please. Of course, and now I want to present 2 disadvantages of composite compared to other kind of solution. Of course, when you want to sell this tank, you need an approval of the tank. So you need, in Europe, you need a CE marking or P marking. P marking for transportable and CE marking for stationary application. If you compare, next slide, please. Next slide, please. Yeah. If you compare the use of composite and the number of tests you need to qualify a tank, you can see that with pure metal tank, type 1, you have a poor number of tests to perform. If you compare to type 5 or type 4, you have plenty of tests. This is also due to the difficulty that the people have to understand the behavior of composite, and because when you characterize metals, you have a relative lower number of figures. If you compare to the composite, which is an anisotropic materials, so you can have plenty of orientation of this fiber. So this is why when you use composite, you have to pay about, I would like to say about 3 times the money that you have to pay to qualify a tank type 1. So use a composite is not an advantage here. It's an advantage for the product, but not as an advantage for the manufacturer. Next slide, please. Another trouble, and it's more due to the behavior that we have, the difference of behavior that we have in composite and in metals. When you use a type 3, type 3 is a liner in metals, thin metal layer, and composite around. You have a difference between the behavior of metals and composite, and especially the difference of expansion coefficient. So when you have the curing process, at the end, when you return to room temperature, you get a gap between the liner and the composite. So you have a thin space between both. Next slide, please. So this space can be observed when you make the first loading of the tank. So here you have some strain gauge on the top of the composite, and you can see you increase the pressure, but during a certain time, you have no strain on the strain gauge on the surface of the composite. This is the time to get contact between liner and composite. And after that, when you get contact liner and composite, you have the deformation of both materials. But this induces a difficulty for the liner. Next slide, please. Here, if you look at what is the behavior when you increase this pressure, what is the behavior of this liner, and what is the behavior of the composite, you can see that during the first part of you don't have any deformation of the composite, but you have already a deformation of the liner. And when you return at the end, due to the possible plastification of the liner could be in compression, external compression, due to the composite. So it looks like if you can have a buckling of the liner. And in fact, if you design a tank, a type-free tank with high pressure, you have a very big trouble in fatigue because it's not possible to get type-free with high pressure use. And there are different kinds of failure. For low pressure, you have a material failure of the tank, but for high pressure, you have a structural failure due to this buckling. So, next slide, please. So very different kind of solution, but no one is good. First, you can say, okay, if I have a buckling, I increase the thickness of my liner to reduce the risk of the buckling. But if you do like that, you increase the mass of the tank, so it's not good. You can increase the yield point of plastification of your liner, but if you do like that, and especially with hydrogen, you can have a risk of retailment of your materials. So it's not possible to do that. The standard doesn't use liner more than 900 MPa in maximum strength. Next. Or you can use fiber with higher stiffness in order to reduce the deformation on both. But it works, but if you do that, you increase the cost of the tank. So today, there is no good solution to solve this problem. The only solution is to use tank under about 350 bar. For 350 bar, you can use metal tank type 3. Above this pressure, it's better to use type 4. Next slide, please. So here it's an example of a company which produce tank, and this number of number of companies is growing. You can see that we have Toyota. Toyota produces his own tank for their car, for the Mirai, for instance. And you can see that in France we have Faurecia. Faurecia is a big provider of tank in France. But the oldest provider of tanks is probably Hexagon Composite, which is a company from Norway. Next slide, please. So, when you look at this graph, and if you are interested to use hydrogen not for car, but for aircraft, you can have this trouble. Here you need the tank at high pressure, and you see that the gravimetric is about 9%. Or if you want to use aircraft with hydrogen, as it is required now, because more and more aircraft is not very well appreciated by from ecological point of view, you need to find a solution to remove kerosene and to use maybe sustainable fuel. And one of them could be hydrogen, where no greenhouse gas. So in that way, there is no solution at room temperature. The only solution you have is to use a cryogenic tank at about 20 Kelvin, so it's very cold. So this tank you can perform can also use composite materials. And today we expect that hydrogen aircraft should be a new holy grail for composite, and especially for composite with high performance. Next slide, please. Here, okay, today there is no hydrogen aircraft, or just some test. And here it's a figure, it's a cost, total cost of money we need to develop this technology in the future to have hydrogen aircraft at around 2050. So we can see that a lot of money will be spent for this kind of development. And I am sure that if there is here some young doctor which is interested by this topic, they can be works on his life, and it should be retired and continue to work on these topics, because it will be a long time to develop this tank. Next slide, please. Hydrogen tank, pure hydrogen tank, have a big trouble because hydrogen should be very limited. So it's around 3,000 kilometers, not more. But here you have some figures who explain the difference, the scenario that we can have on the demand of hydrogen in the future. But we can see that it will be not possible to cross the Atlantic, for instance, with hydrogen aircraft. It's today not possible. So the way to cross hydrogen with sustainable aircraft will be to use a double fuel technology, sustainable fuel, and hydrogen. Hydrogen to start and to take off, and maybe during the transfer to use sustainable fuel. Next slide, please. Even if you are limited in range, you can see on this figure that about today, 90% of the range of a flight is less than 3,000 kilometers. This 90% of flight have a consumption of about 50% of the fuel. So if we work on hydrogen aircraft, in the future we can save 50% of the fuel by using hydrogen. Of course, for long range, we need another solution. It's not possible to use cryogenic gas today. Next slide. So there is some thinking about that, and in my lab we are working in this figure. Okay, today the people think that the cryogenic is the best solution to transport hydrogen. But in fact, this induces a lot of trouble, because liquid hydrogen is very difficult to manage. So, and some of the people, and especially in Dassault in France, thinks that it could be possible to use gas, but cooling gas, at about 80 degrees Celsius, minus LT or minus 100 degrees Celsius, and also with high pressure. So you can see that in this figure, if you are at minus 120, the gravimetric that you have is about 60 grams per liter. So it's very close from the gravimetry that you have with hydrogen, liquid hydrogen. So in fact, if you cool your hydrogen and you increase the pressure, you can have a gravimetry, so the volume of the tank will be not bigger, but the volume of the tank you can have in liquid. And it is more easier to manage the feeling with hydrogen under pressure, but the feeling with liquid hydrogen. Next slide, please. So this is my conclusion. Next slide. Conclusion. What we can see, in different kind of sector, there is a requirement for the materials against corrosion. We need very high mechanical performance. We need a thermal performance, and we need light materials. This is why we believe, and I believe, that composite has a bright future ahead of them. Next slide, and just a small part of HUMMER. So, zero carbon aircraft is already existing. I use this with my grandson. Thank you.
Thank you very much, Prof. Bapak-bapak, ada pertanyaan? Saya tahu. Siap, satu lagi kalau boleh, kalau ada. Dua. Izin dua saja karena waktunya mepet. So, there is 2 questions for you, Prof. Please, Pak.
Thank you very much.
Please introduce yourself first.
Okay, my name is Trisna Sumardi. I'm a lecturer in University of Indonesia. I'm also graduate Leko Central de Paris. Thank you very much for your very extraordinary presentation about the use of composites in Sameton, Biang, for high temperature applications and also for the high strengths. Is the fiber you use in all your project is carbon or other potential fiber? And the second one is what about the resin or the matrix you use here? Is epoxy or other potential? Okay. And the third question is about what is the potential of the green composites of natural composite in this case? It's your predictions. It's have potential for the high temperatures and high strength application in, for example, in the hydrogen pressure vessels or other application. Thank you very much.
Please, Prof.
Thank you. So about the fiber, it's very depending of the application. For onboard application, we need to use very high pressure. As I showed you, it's about 700 bar. So at this pressure, if you want to have a light tank, the only way is to use carbon fiber. For onboard application, all the tanks are in carbon, use carbon fiber. For other kind of application, and especially for stationary application, for instance, at my tech company, we develop a glass fiber tank because the pressure is just the pressure that we get after the electrolyzer. Electrolyzer produce hydrogen usually at 30 bar or 60 bar, and so we store this hydrogen without any compression at 60 bar. So at this kind of pressure, and because it's a stationary application, we can use glass fiber. And also we try to use natural fiber for this tank, because if we use carbon fiber, it's not already good from greenhouse effect, because you produce a greenhouse gas if you perform this with carbon fiber. But it's with with green composite, it's very limited in pressure. It's not possible to use for high pressure. So for low pressure stationary application, glass, natural fiber could be used, and we have already tried to develop a tank with natural fiber. And the last question is about type of resin we use. We use a thermosetting matrix for type 4, and it's an epoxy matrix, because also we need to have a good resistance to fatigue and so on. So this is why we continue to use thermosetting and especially epoxy. There is a new development for what we call Type 5 tank. Type 5 tank, it's a tank where there is no liner, and we can use thermoplastic matrix with fiber inside. But today, it is not very interesting today. There is no, it's very difficult to find on the market Type 5 because the development is not really finished. So today, Type 4 with thermosetting matrix, carbon fiber is the best for onboard transportation, and for other kind of application, you can use glass or you can use natural fiber.
Please.
One more question is very important. I have forget to ask you about the. Do you use also the pre-impregnations, pre-breaks for the carbon and epoxy, for the easy to implement it in the manufacturing of components? Because it is very interesting for the hydrogen storage and also the nuclear station applications. So I want to ask about how far the implementation of the pre-impregnations composite for carbon epoxy. Thank you very much.
So that's right, you're right. There is two technologies, the wet and the dry fiber. For economical point of view, the wet process is less expensive, but from quality of the materials, the dry production by using prepreg, if this is your question, is more interesting. And for aircraft application, the tank we perform for this kind of application that we develop at a low temperature is made with prepreg and fiber with very high strength. We use a fiber at 7,000 MPa on strength. So it's very, very tough, very high. And in this way, we use the prepreg because the cost is not very important today. So quality is important.
Thank you, Prof. It looks like for me you have found a companion for your lunch, yeah. You will have a big discussion with him. Okay, the other question, please. Yeah, please for the simple question. Thank you.
Yeah, don't worry, I only have two questions. My name is Firman from ITB, Institut Teknologi Bandung. Yeah, we have been talk a lot about hydrogen, about the potential. But as we know that hydrogen is not the primary energy source or primary fuel, right? And it will be developed as like along with electricity and batteries as energy storage. In your opinion, how this hydrogen will develop, maybe specifically in Indonesia that you mentioned, we have a lot of islands, whether the supergrid will be the best for our electricity transmission or the chemical storage that transport energy between islands will be better. I mean, I'm asking your opinion on our nature. And the second one, interesting about the composite as the material for hydrogen tanks. As we know, as far as I concerned, that hydrogen storage in tank will have a concern in embrittlement or by hydrogen penetrating to the materials. Does that will it be happening also in composite, and what kind of countermeasure have you been using, like for coating and so on? That's only two questions from me. Thank you.
Thank you.
Okay. Yes. So hydrogen, we can say that it is not the beginning of the story, but it looks like the beginning of the story. Because in order to continue to develop this technology in the world, not only in Indonesia or in France, I think we need to reduce the cost of the fuel cells, convert hydrogen in electricity, and also to reduce the cost of electrolyzer, to convert water in hydrogen. So today, due to the big plants that are developing in Europe, in US, and in Asia, and especially in China, we can assume that the cost of the hydrogen electrolyzer and the cost of the fuel cell will be reduced in the future. So the cost is the main problem today. If you buy a car or if you buy a bus with hydrogen, you will pay about 2 or 3 times more than with a classical technology. So we have to make a progress of the cost. And for island, and especially for Indonesia and for a lot of countries where we have island, for instance, in France, we have in the west part, we have small island, and there is a lot of projects because the idea is that you can produce locally your own energy by using, for instance, PV cells, wind, and use your energy where you are. Of course, maybe it's a dream, maybe it will be not possible for all cases, but the main idea is there. And of course, for the transportation of this hydrogen, for long transportation, maybe pressure vessel is not the good solution, but pipes, it could be a solution. And also you can use ammonia, you can use other kind of product, liquid, organic, hydride, like that. There's plenty. Every week, there is some people say, I find the solution to transport hydrogen. In fact, you find a solution to improve sometimes. So this is the first question. I don't remember the last one. Yeah.
The hydrogen embrittlement.
So with type 4, there is now a long experience of what kind of material you can use in the tank. With type 4, the only problem where you can have embrittlement is in a boss, because metal, you use metal boss here. But in fact, we use aluminium, different kind of aluminium, which is well used for this kind of application. We don't see any problem with the liner, with polymer liner or composite materials. We see some problem that if you have a fast depressurization of the liner, you can have some bubble of hydrogen inside the liner, and so you can get a crush of the liner. So this is why when you get a tank, the manufacturer told that you can discharge this tank with only 10 bar per minute. If you go faster, you have a risk with this kind of type 4 tank. Okay, thank you.
Thank you, thank you. So sorry, audience. I know some people still have some question, but we have time limitation. So I think you still can communicate or discuss with professor after this session, or maybe using email, WhatsApp, or whatsoever, right? Okay. So for the good keynote speech and for the discussion, let's make a big applause. Thank you so much. Prof, thank you so much. Thank you so much. Acara saya kembalikan ke pembawa acara. Mangga?
Penyerahan plakat sama Bapak atau Pak Aryo? Oke. Kepada Pak Aryo untuk dimohon ke depan, Mak.
Okay, thank you for Professor Dominic Perix. And mohon informasi, izin menginformasikan bagi Bapak Ibu untuk coffee break sudah tersedia dan dimohon untuk barang-barang penting seperti handphone dan peralatan lainnya untuk dibawa karena ruangan akan segera di breakout. Terima kasih. Oh ya.
Satu lagi pengumuman bagi para pemapar atau presenter yang merasa waktunya tidak cocok, tolong hubungin panitia. Kami coba usahakan, gitu. Ya, terima kasih.